Throughout human history, we have constantly come up with new ways to play games. The game of pinball has been constantly evolving over the past 100 years. From the introduction and refinement of flippers, to electrification, and further to solid-state electronics and dot matrix displays. Unfortunately for pinheads everywhere, a threat emerged, which occurred in the late 20th century, which almost ended the game as we know it. As video game technology improved, the ability to play games anywhere greatly detracted from the allure of the arcade. Fortunately, this explosion technology also brought with it an evolution in pinball. Now, pinball was everywhere again. However, no matter how good the software looks or is, playing with one of these or one of these just isn't the same. Pinheads everywhere wanted to play pinball the old-fashioned way. All that was needed was one more evolution. One that will take pinball to the modern era. Let us introduce you to this evolution, our 3D Pinball project.
Hi, I'm Jeffrey Jones.
Hey, I'm Mike Watson.
And I'm Jonathan Beatty, and we are
Team 3D Pinball.
Here are our engineering requirements. The first requirement is 3D facial recognition and tracking. We utilize a 360 Connect camera to track a face from 1 meter away. Our second engineering requirement is a pinball frame rate. The refresh rate of the pinball gameplay must be above 15 frames per second. Our third engineering requirement is the adjustable pinball cabinet height. The cabinet must adjust at least a half an inch. The fourth engineering requirement is a cold start boot. The goal of this requirement is to start in 40 seconds.
For our fifth engineering requirement, we utilize Future Pinball software, which loads and plays all our pinball gameplay. For our sixth engineering requirement, we required a minimum of 4 pinball tables that the user can select and play from. Our seventh requirement instituted pinball cabinet heat control. If the cabinet reaches 52 degrees Celsius, then a minimum of 20 cubic feet per meter will initiate to cool the inside of the cabinet.
Our eighth engineering requirement involved button response and plunger response, which we set to 100 milliseconds to ensure that there would be no lag between the user and the pinball table. For our ninth engineering requirement was related to plunger retraction speed. We set that to 1 second to ensure that it wouldn't be sticking out during gameplay that someone could accidentally walk into. For our 10th engineering requirement related to our audio system, in which case we set the minimum audio pressure to 70 decibels to ensure that it could project sound throughout the crowd of people during gameplay.
Here is our block diagram that we developed for a 3D pinball cabinet. Today I will be talking about the computer block, the facial recognition code block, the gameplay code block, and the enclosure block. First, we'll start with the heart of the system, which is our computer block. Our computer block has 6 different components. This consists of a power supply, RAM, a CPU, GPU, an SSD, and lastly, the motherboard. The computer pretty much interacts with every block at an optimal level. And you can clearly see this when you look at the GPU. For instance, it's a Radeon R9X series, and we specifically chose it for all of our 3D imaging and processing. Speaking of which, we'll go on to our facial recognition block. For the facial recognition block, we specifically interfaced with a 360 Connect camera, which tracked the user in XYZ space. Depending on where the user was, we implemented his position into our gameplay code so that the game adjusted in 3D space so that it appeared stereoscopic 3D, similar to how the Nintendo 3DS interacts. Next, we'll go on to the gameplay code. For the gameplay code, it was a pretty hard challenge, mainly because of all the scripting that was involved. For instance, we currently have approximately 30 different tables, which all interface with the future pinball front end, and all use advanced 3D imaging. So you can see it was pretty much a big hassle. But we got it together, and as you can see in our previous demos, it looks pretty fantastic. Moving on, we'll go to the enclosure block. The enclosure block was no easy feat either. We picked out all the wood ourselves and cut all of the wood with a laser cutter. The laser cut was based off of a bunch of SolidWorks files that we developed, which went through 4 different rounds to even develop the different blueprints that we wanted to choose. On top of that, we decided to coat it with a primer and then 2 layers of a flat black coat, finally adding a clear coat. This was to make sure that the finish really looked nice on our cabinet. On top of that, we added 4 different metal pinball cabinet legs, a metal enclosure which came around the glass which goes on top of the gameplay field, and a metal hinge so that the backsplash may hinge just like a traditional pinball cabinet.
I know all of you have been admiring our little block diagram, so I'm going to have your focus shift up a little bit over to the button section. So notice that we have flippers, coin op, etch your ball button. You probably can't read any of that, but what that means is that we have a pinball cabinet that has every button you can experience in any type of pinball cabinet you see in arcades, bars, if you're over 21, if you're under 21, whatever. I'm not judging. But the point is that we wanted to simulate a full experience that you would see in any other pinball cabinet. That's why we have these whole range of options for user. Now, this is only just regular tap buttons. We also have an analog plunger, so when you pull it back and release it, it will actually create a force unique than a digital plunger, which just says, hey, I've been hit. On top of that, we also have something called an accelerometer, where if you tilt it, nudge it, it will actually affect the gameplay and affect the ball depending on how you tilt it, nudge it, just like you would experience in a regular pinball cabinet. So while all these are inputs that users can interact with, they don't really mean anything until we do something with it, which is what leads to my next block. As you can see, each of these run into something called a microcontroller, and while it may show just one, we actually have 2. One is called Freescale, and the other one is called a teensy. The reason why we use both is honestly because of a technicality, but to break it down, we use a teensy for just the buttons that you see way up top, versus the Freescale has an accelerometer built into it, and we can easily apply the analog plunger. So what that means is that we had to develop 2 unique codes for both. So to ease that up a little bit, we decided to go with an approach that a lot of gamers are familiar with, which is using a keyboard to play games with. So if you never played any computer game whatsoever, you know your A, B, C, anything like that, just characters, by pressing one of those, you'll get a response in-game. With that theory in mind, we actually had the microcontroller act like a keyboard. It's not a natural keyboard, keep in mind, but it acts like a keyboard. So when the computer actually sees a response, it thinks the keyboard's responding or getting a message from it. This leads to a gameplay experience where you hit a flipper button, anything like that, and you'll get an actual response.
Our last few blocks are the fan controller, the sound block, the camera block, and the monitor block. For the fan controller, we used a thermoresistor and a voltage divider configuration with a comparator. The comparator sent a voltage to a MOSFET which allowed current into a fan such that As the temperature increased in the enclosure, the fan speed increased. For the camera block, we used a 360 Connect camera. The important parts being that it could take in 30 frames per second imaging for the 3D facial tracking, and it could tilt up or down by 20 degrees. The monitor block was a gameplay, DMD, and backsplash displays. The gameplay and backsplash used HDMI cables, while the DMD used a DVI cable. The sound block was a 200 watt acoustic audio system, which allowed us to play our 70 decibel sound really nicely, which could go up to 120-ish if we cranked it up.